Sometimes you'll be asked to turn a complex number in rectangular form into polar form, and you'll notice that there's no real special angles in here. All those radical 3/2s and 1/2s, those nice numbers that make the angles good, we don't have those right here. So we're going to get something that looks a little bit weird at first. The same rules apply as if you had special angles. You just can't finish simplifying that arctangent part. And I'll show you what we mean as we get into this. But let's clear up the easy stuff first. The real part of this one is -3. The imaginary part is -2. The modulus, if you remember how modulus is calculated, it is the square root of the real part squared plus the imaginary part squared. If you simplify that for this one, you'll see we get radical 13. Okay, so easy stuff's out of the way. Now we're getting into the argument and the principal argument. And here's where I think, if you're looking at this video for some help on the homework, this is probably where you went off the rails. The argument, remember, that's the angle. And we use our equation conversion from rectangular to polar coordinates for this one. Inverse tangent of theta equals y over x, which for us on a complex plane is imaginary part over real part. Okay, well, what's the imaginary part? For us, that's -2. And the real part for us is -3. So I've got tangent of theta equals 2/3. Well, I could kind of point to where that is on a circle, but not exactly. I don't exactly know where this is true. So what we have to do here, you might find a little unsatisfying, but we're going to do this. We're going to say theta equals the inverse tangent, the arctangent of 2/3. And that's simply how we have to leave this. Now, before we enter that in right here for our argument, watch out for one more thing. I want you to pull out your calculator, see what it gives you for inverse tangent of 2/3. Okay, I'm going to type that into my calculator right here, see what we get. Okay, great. So what I got, and I'm going to use degrees because it's a little more obvious to everyone where it'll be. I got 33.7 degrees. Well, where is that? If this is 30 degrees right here, okay, I'm going to be just a little more than that. So I'm looking at somewhere like this, okay, somewhere in between these special angles. But the important part is it's in quadrant 1. Are we in quadrant 1 according to the rectangular form up here? Rectangular form says, nope, you are in quadrant 3. So we have to find some way of changing this angle that we got, 33.7 degrees, to this one over here, a quadrant 3 angle, which will also give us a tangent equal to 2/3. So how do we do that? Well, I would just ask you, what is the angular distance between these two lines? Right? How do we do that? It's just plus pi. That's how you just get between them. So what I'm going to do is I'm going to fidget with this a little bit, and I'm going to say, okay, inverse tangent 2/3 is quadrant 1. I don't like that. But if I add pi to it, now I am a quadrant 3 angle. So this is what you have to do right here. You have to say, is this inverse tangent, according to a calculator, going to land me in the right place? Because if the computer says, oh, inverse tangent 2/3, that's quadrant 1, you're wrong. You have to add that plus pi in manually yourself. Last part, let's talk about this guy right here. Principal arguments. Arg with a capital A. We need to use the interval -pi to pi. And if you'll notice, the angle that I've just drawn in purple is bigger than pi. Right? It has to be. We just added pi to it, so it's going to be bigger than pi. So we need to find a coterminal angle, which is actually not bigger than pi. It's smaller than pi. It can be as low as -pi. And all you do here is, this is not too hard. You say, in this case, the principal argument of z is equal to the argument of z minus 2 pi. That is not always true, but it is true when you are in quadrant 3, or I would say quadrant 4. When you're in those two quadrants, you're going to need to subtract off 2 pi to get yourself into the interval -pi to pi. Well, what is that? That's going to give us argument of z, capital A, equals inverse tangent of 2/3, same as before, minus 2 pi. You got that plus pi, and then minus 2 pi gives you a minus pi over all. Okay, so this is going to be your principal arguments. And I'm sorry for the hassle. There's reasons principal arguments are a thing that we have to watch out for. They just are. Now, last part, when you're writing this in polar coordinates, here's what we have to do here. You're going to keep r as is, right? R is radical 13. And you're going to multiply it by the cosine of theta. And then you're going to say plus I sine of theta. Well, theta is this thing, right? This is theta, this argument. So yes, this answer will get a little big, and it's because we have inverse tangents that we can't resolve. But that's how you have to write it in polar form. Usually we will not be dealing with integer values for real and imaginary parts. We're going to be dealing with values that give you nice or nicer special angles that simplify pretty well. Let's do one more thing, and let's plot this point on our graph. Okay, so where would this actually land on here? I know I'm in quadrant 3. And you can kind of cheat a little bit and just use your rectangular coordinates up here to try to figure out where you're going, but that's only going to get you so close. I mean, I might guess here, but I'm not really sure. That's a pretty good guess. Using polar coordinates, the way I would do this is I would say, okay, radical 13. What is radical 13 anyway? Calculator might come in handy. I mean, I know it's approximately more than 3 and less than 4, but the calculator says it is 3.6. Okay, and we already know that the angle is somewhere in here, right? 33 degrees or so. And 3.6 looks like it's kind of halfway in here. So there's my point. That's how I would graph it using polar coordinates without cheating and looking at the rectangular coordinates. Okay, so not bad. And you'll notice that the graph is actually very lenient in this problem when you're plotting these points, because I know this isn't nice integer numbers. They don't fall exactly on grid lines, so we've got to be a little forgiving.